Okay, I've just pressed record so I can start up the lesson, but I'll pause it in a moment. So what you have on the board right now, hello everybody, by the way. I sort of greeted half of you when you came in and half of you I just ignored rudely, which is fine. For me it is anyway. So on the board here, we just have a little starter problem. So write it down. I think you've got enough information there to work out what question and question could be, I reckon. In fact, you can do it without a calculator. But if you want to get out your cheat sheet, you're welcome to. You know what I'm talking about. So how about I just give you, this is all right angle trigonometry, and there's method in my madness, okay? So just do the problem and we're gonna revisit it a little bit later, okay? So see if you can work out what question and question mark is, and we'll go from there. I'm gonna pause the recording, just otherwise it's just dead space. Okay, so here's the problem. Actually, it might be worth just checking out for everybody. Who did it using Pythagoras' theorem?
I'm doing it with the sine rule.
That's okay. Sine rule is probably the least efficient way, but we'll talk about that in a second. You did it using Pythag? Okay, so a couple of people used. Okay, so if you did use Pythagoras' theorem, it's legitimate. It's probably not the most efficient, but it's a very reasonable approach to take because they're fairly small numbers and you can probably do it in your head. The square root of 2 is 2, 1 squared is 1, 1 plus what is equal to 2, 1, so the other side must be the square root of 1, which is 1. So you can do it in your head, right? That's fine, especially if you did it in your head. I'll do it the trigonometric way, but in my head as well, in a sense that I know that the sine and cosine of 45 degrees is the same, and the sine of cosine of 45 degrees is root 2 on 2. I'll just write it here for a second. But this is one of those spaces where if you remember originally that root 2 on 2 came from rationalizing 1 on root 2, then you've got your opposite over your hypotenuse already. So personally, I would have gone, that must be 1, like so.
That's what I did, but wouldn't you do it with the 1 on the outside?
You could have used cosine and said adjacent over hypotenuse, but that wouldn't have got, oh yeah, sorry, yeah, tan, yeah, absolutely. As long as you know that tan of 45 degrees is 1, and it should be on your chart, then using that would get you exactly the same spot. Perfect. There's one other thing you could do as well. If you used sine of 45, then if you started off with root 2 on 2, then that has to be the opposite. That has to be the hypotenuse, but it ain't. Yeah, the hypotenuse is root 2, so this has to be root 2. It isn't, so you have to manipulate it until it is. But you know what? Can I just give a shout out to Archie, who said, why wouldn't you use tan? Because that's easier, you idiot. Absolutely true. If I'd used tan, I would have said, what over 1 equals 1, and the answer would have been 1. But I'm even going to go even simpler than Archie. And I'm going to say that if you look at this triangle here, this right angle triangle here, we know that's 90, it has to be. We know that's 45, it has to be. So what's that one? So what kind of triangle have we got? So if one leg is 1, what's the other leg? Do you know? Okay. So there's a bunch of ways you could do it, but can you see how that efficiency, just by tool selection, you can get there faster, okay? And you know what? I just want to put it out there that when I constructed this problem, it was thinking about sine and cosine. So when I put my own brain in that spot where I said, how are they going to solve this? Oh, they'll solve it using sine. And then when Zoe said, I use Pythagoras, I went, that's not what I thought you'd do. Oh, that's fine, it's fair enough. And then Archie said, why'd you use sine for? Use tan. Well, that's not what I did. Well, no, that's actually better. And then as I was thinking about what makes it better, I went, oh, but of course it has to be 1 because it's an isosceles triangle anyway. So don't think I sit here saying I always select the right tool and you just need to aspire to be like me because you probably can't afford the weight gain. All you need to do is you just need to just step back from the problem and think carefully about what is the best method. Honestly, in a mercenary style, every time you step back and think carefully about it, you're going to gain yourself time in an exam that can be allocated to other marks. Archie.
With the isosceles method,
yeah.
what's the notation for working out that?
I wouldn't bother really. This is such a simplistic sort of thing. In terms of the exams, you know that I'm a really big fan of communication. Please don't forget that the IB are not, in that they just want you to put some calculations down and then you'll get the right answer kind of thing. And you can get part marks if your calculations go right. But ultimately, they're not looking for really solid notation work. Yeah. So, and at this stage, you're now in year 12, there are some things that you can just get out. Yeah. And you know me. So if I'm telling you that, it must be okay, because you know how strong I am on communication. On the other side, I'm hoping you might have got root 3. I don't know what method you use. You could use Archie's method of tan, my method of my method of sine. It's up to you. Or Zoe's method of Pythag. You'll get there. You'll get root 3. Oops, I used the right same color. So that's just for those who didn't get there. If I'm looking at sine of 60 degrees, then the sine of 60 is opposite over hypotenuse. We know from our table or from our own brain that that's root 3 on 2. So obviously it's the opposite that's missing. So that therefore must be root 3, because the 2 is already nice and neatly there for us. So that's root 3. And you know what? I'm going to give you 30 seconds to write down this next bit as well. It's interesting what people write sometimes, so I won't guide you through it. The big triangle, so I'm talking about the bit I'm tracing out now, has a side length of root 2 and a side length of 2. Can you please write underneath what the side length of that third side is? The third side, this one. I'll give you to the count of 10 to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we know that anything multiplied by 1 is just itself. Therefore, the length of that missing length of the triangle is? No, well done. I was just trying to trick you there. It's 1 plus root 3. Yeah, but it's a day ending in Y, so I feel like it's my obligation to do so. 1 plus root 3, okay? Can you use your calculators and write next to that a approximation to how many significant figures? Yep, go. Write it down. Without your calculator? Yeah, good lad. Rosie wrote down the approximation without even using her calculator. That's why she's at the top of the class. Good boy. You mean use your phone instead? And what? And on, look, if you actually called, are you called Siri? Yeah, phone a friend? Yeah, can't do that in the exam. 3, 2, 1. Okay, so 2.73. 2.73, yep, to 3 significant figures. So that's okay. That's the side length to 3 significant figures. Now, for really good reason, I'm just going to leave that. That's like your starter problem, but we're actually going to come back to it later in the lesson for really good reasons. So I'm about to do a bit of a non sequitur and skip to something else. Zoe, I'm sorry to be boring you. That's okay. Whilst yawning. Okay, so here we go. This is what I promised you, Zoe. I'm just going to say it rather than write it because it'll be on the recording. Zoe walks for 1 kilometre north, 30 degrees east. Draw the diagram. Zoe walks for 1 kilometre north, 30 degrees east. I will write it down as well. I just wanted you to get stuck into it. Okay. Hopefully you've got a diagram. I don't have quite enough time to come around and check individuals, but if you've done it well, it'll look something like this. A northeast little line here. So we know north is pointing up. and east is pointing to the right. And so 30 degrees would be about there, wouldn't it? So the 30 would be in there. And let's call it X marks the spot, because we all know that that Zoe is actually really a pirate. You need to work out exactly how far Zoe has traveled north and east. Sorry, it was just an accident. Better? Okay, so north, 30 degrees east. X marks the spot. How far north and how far east has Zoe walked? We know that she's traveled 1 kilometer directly as the crow flies, but if the crow was walking, what would the crow be doing? How far east, how far north? Can I remind you, please, that one good thing to do once you've got a diagram of the situation is to extract the triangle, label it with variables for the things you don't know, and then work it out from there. You shouldn't need one because you've got your exact values there anyway, and that's fine for what we're doing here. Okay, stop. Whatever you're doing, stop. Who did that to start with? As I suspected. That's a very reasonable thing to do. Just listening in for this bit. Again, for reasons that will become clearer, I'm now going to get you to do it this way. Should give us the same value, shouldn't it? Oops. And what angle would go in here then, please? Who said that's what I did? Randos? 60 degrees in here. So that's correct, 60 degrees. So we've got a 1 kilometer hypotenuse, and we can label this E for, we'll not use capital letters, E for east and N for north, and you can work out what E and N is, right? So for those of you that started off with 30, can I just say that that's a smart way to do it, because that was one less calculation, wasn't it? Just so happens it doesn't fit my narrative, so I'm making you do it. I'll explain why later. It'll all come together. Sorry? Is this a valid narrative? I can't tell if there's disappointment or shock. Well, I thought it was a poor impersonation to start with, and I was trying to process that in terms of, I've seen you do an excellent Brenda, but that was, I would say, a substandard Richard. But my mathematics, you're just taking the mickey out of what I said. Ah, I see difference. Yeah. Yes, okay. I mean, I would have probably extracted the triangle out just purely, but that's just the thing. Sorry, you've got 1 more minute. Don't feel like you have to be here for the whole lesson. Just sneak off whenever you want to. You've got the idea of how it's used, though. Yeah. Lovely bunch of students. New computer science teacher, and he does my programming class over at high school as well. 15 seconds left to wrap it up. Yep. And let's face it, this particular problem will be the gift that keeps on giving too. So it works on lots of levels. Zoe, well done.
is equal to.
Did you get that?
Same one as you.
Okay. Might need your focus now. This is all putting some puzzle pieces together here. So each step hopefully is reasonable to do. So you've got east is equal to a half and north is equal to √3 on 2. And east being a half is exactly what the cos of 60 is. And north is exactly what the sine of 60 is. Because I've used a hypotenuse of 1, it's just going to be the sine and cosine value. That's pretty good. I'm going to give you a different problem. I will tie it all together in a second. I do actually really need your focus on this because these are little puzzle pieces that we're putting together. So if you're devoting even part of your processing time to coming up with the next comment or talking about something that's not to do with your maths, I think you're going to struggle to draw it all together towards the end. So for your benefit, please don't do that. So Zoe walks for 1 kilometre north, 30 degrees east. Nope. West. Thanks. 1 kilometre north, 30 degrees west. How far north? How far east? Draw the triangle first. So draw the diagram first, extract the triangle, solve it really quickly. It should say west. Yeah, west. Oh, sorry. Thank you. How far north, how far west? So draw your little crosshairs, draw it in again. Just focus on this, yeah? If you're devoting brain cycles to, I wonder why it's a crosshairs, how many brain cycles are trying to work out exactly how these problems are linked and where Richard might be going with it all? No. The bonus problem is you focusing on your work. I'm going to zoom that out now because I want to do a little bit more work as we go along. You know what? I'm only going to give you another 30 seconds or so to do that. And if I'm only giving you 30 seconds, perhaps that's because there's an efficiency again that you can get from linking the problems together rather than calculating them all out by hand, maybe. Okay, that's your 30 seconds gone. So really quickly, if I draw my compass bearings here, I've gone north 30 degrees west. So the actual diagram looks like that. And then if I extract it into the triangle, I'm just being really rough here with my triangle work, sorry. I'm going to have a 60-degree triangle. I'm going to have a 1 kilometre hypotenuse. So in fact, I've got exactly the same triangle as before, haven't I? It's just facing backwards. So I reckon I can really quickly flick over to this page and I can see that I got the base being a half and the height being √3 on 2. And I'm going to get the same thing here as well. I'm going to get this being √3, sorry, beg your pardon. Thinking too quickly. This is going to be a half or a 0.5, and this is going to be √3 on 2, which is what, about 0.86, something like that, because √3 is 1.7. So 0.8, something like that. Okay, is that okay so far? We can do that quickly because we can rely on results we just figured out. That's all I'm saying. It's just it's the same triangle as backwards. Okay, now let's talk about directed numbers. Numbers by themselves have two properties, do they not? They have a size, which the official name for that is magnitude, and it has a direction, positive or negative. So what happens if we introduce the concept of not just magnitude, but direction into our calculations here? So what if, oh, by the way, this is cos 60, and that is sine 60 as well, right? So what happens if we start talking about those concepts of north, south, east, and west, but relative to a positive and negative, where north and east is positive from the starting point, and south and west is negative according to the starting point? Yeah, Archie just connected there. It's like a graph. It's like the Cartesian plane, right? So the Cartesian plane has an origin. That's where Zoe started walking. For the northeast, we sort of did that. Sorry, that's not steep enough. We sort of did that a little bit. And here, we just traveled like in the opposite direction, right? So it's 60 degrees, but backwards. So if this distance here was 0.5 and this distance here was √3/2, if we use northeast positive, southwest negative, what distance relative to, with direction added to it, how far north has Zoe traveled here? It's the same, √3/2, right? That's √3/2. How far has Zoe walked with using directed numbers? -0.5. So when we go backwards or down, we simply use the same values, but we put a negative on them. If we travel up or to the right, we have the same values, but they're positive, but they are a mirror of each other, because you can see there, let me zoom up so you can see it nice and clearly. My dodgy drawings aside, it's a mirror over that y-axis. Okay, it's a mirror. And I deliberately do call it an x and y axis because effectively that's how it works, with the center being the origin and north being positive movement on the y-axis, east being positive movement on the x-axis, south being negative movement on the y-axis, and west being negative movement on the west axis. Let's pull it all together a little bit more. If I now zoom up really big here, this is a coordinate. This coordinate, by the very definition of coordinates, is just the x distance traveled and the y distance traveled, the north, and sorry, I'll do it around the right way, the east and the north distance. Okay, so if you remember, 0.5 was just the cosine of 60 degrees. √3/2, the y distance, was just the sine of 60 degrees. So it's a coordinate point, now utilizing our understanding of the angle away from the x-axis. Okay, so the angle away from the x-axis is 60 degrees, and therefore this coordinate is cos 60 sine 60. Okay, the x distance traveled and the y distance traveled. Now, what about this one over here? Now, we know, I'm gonna have to go all messy here so we can sort of draw it really clearly. The coordinates are √3/2 and, sorry, wrong way around. The coordinates are -0.5 and positive √3/2. That is negative cos 60 and positive sine 60. Good so far? Well, this is really good for one reason. If we now, everything we've done has reoriented our thinking from north, south, east, west to directions that are relative to the x and y axis. So this is, oops, I meant to use the pointer. This is relative to the y-axis. This is relative to the x-axis. So is this, and so is this. We've just put direction on it to help us notate what's going on. So we should do the same thing for the angle as well. So what we do is we talk about the angle away from the x-axis, therefore, as being this. What's that going to be? If that little angle there is 60 and the whole angle is 180, the blue angle is 120. So this means that the negative cosine of 60 is actually a new value that we've never had before, and that's the cosine of an angle above 90. The sine of 120 is exactly the same as the sine of 60. Okay? So now we're able to extend our understanding of what does sine and cosine mean, angles in a right angle triangle, to sine and cosine are now extended to multiple kinds of angles. The cosine of 120 degrees makes sense. The question of what does cosine of 120 mean is this. It's 120 is the angle away from the x-axis. If I have a look at what right angle triangle it makes when I stop, here it is here. If this is the right angle triangle that's made with the x-axis and the y-axis, then the angle inside is just 60. So I can use the sine and cosine of 60 to work out my number, and I can use where I land as my direction. Is it positive or negative? For directed numbers. Sorry, I shouldn't have said direction because that's confusing with north, south, east, west. I can use where it lands to work out whether it's positive or negative. Okay, so because it's landed here to the left of the x-axis, we know that numbers to the left of the x-axis are negative, which means the cosine of 120, which lands over here, will be a negative value. If you've got your calculator, let's quickly have a look at it, and then I'll take questions. Can you please get your calculator out? And you should know this value already, but can you please go cosine 60 equals? Okay, clear that and go cosine 120 equals. Same value, but negative. In other words, going back to what we were saying before, the fact that Zoe's traveled 1 kilometer, whether she went in that direction, comes out to the same values of, horizontal and vertical movement. She's either landed here or landed here, but in both cases, she's traveled 1 kilometer. And in both cases, it was a half a kilometer sideways, if you like, and root 3 on 2 upways in both circumstances. That makes sense when you think about Zoe walking for a kilometer in those directions. All we're saying is that if we add a relative nature to it, so this is positive and this is negative, then relatively from the origin, from her starting point, she's kind of, that 0.5 means she's traveled back 0.5, and then she's traveled up by whatever root 3 on 2 is, 0.86, whatever it is. Okay, and you'll find also on your calculator, if you go the sine of 60, you'll get a value, and then if you go the sine of 120, you'll get the same, exactly the same value, because it's exactly the same distance up. She hasn't changed direction there, has she? She's gone up in both instances.
So in the same way that negative cosine 60 is equal to cosine 120 and sine 60 is equal to sine 120. On the other side, is it the same thing? Cosine of 60 is equal to
negative sine 100, yeah, negative cosine of 120, yeah. So I don't want to dwell there, Jeremy, because I just want to say that these are the angles we're used to. They're all of these angles between here and here, apart from 0 and 90, between here and here, all of these angles are things that we are used to because they're right angle trig. We know what the sine of 30 is. We know what the sine of 60 is, and the tan, etc. We know all of that. That's fine. So we call these the reference angles, the angles that come from right angle triangles that are reference angles. So what we're saying is that beyond, or including 90, but beyond 90, we can still make meaning out of sine and cosine and tan by referring to the reference angle. And we're going to do, this is, believe it or not, this is the soft launch into the unit circle, but we're not doing unit circle today. We're doing it for another reason. All I want you to take away from this right now is this. Does it make sense, therefore, that we can talk about the sine of 120 or the cosine of 120?
Why the cosine rule works the way it does is you can either have an obtuse or an acute angle.
You can, but you know what? Not quite, but we're going to do that today. Jeremy, I remember a couple of people around the room saying, oh, I've got, when they were trying to work out an angle, they did numbers divided by other numbers and they got negative 0.47 or something like that. And they sort of went, oh, I've got a negative, is that right? And I said, yeah, just deal with it. So go second function cosine and deal with it and it'll be fine. I went, oh, okay. And of course they got 110 degrees or 117 degrees or whatever. Why can it accept negative numbers? Because, and why did I know it would be something like 117? Because I know that 117 would fall into this area, and if it falls in this area, I know that cosine would be negative. So it all links up. So now when we use, not one person, I didn't expect you to, not one person turned to me and said, wait, you want me to do the cosine of 105 degrees? That's not possible. It doesn't fit in a right angle triangle. No one said that, and I didn't expect you to. But honestly, we were using cosine in ways that we may not have understood at the time. We were just putting it into our calculator without actually saying, well, why would it give me negative 0.5 or why would it give me negative 0.6? And this is why. Does that kind of make sense? We're going to go over this so often that you'll get into it, but this is just a soft launch into it. Ambrosia. If I think it's a long answer, I might just bookmark it there, that's all.
Oh, no, this is a short answer. I may need to point because I'm not good at doing the whole. I'm not going to just point on the wall. Like, so this may seem really stupid, but if that's like that angle, wait, hang on. Why can't you just do it this way as well?
Okay, kind of, I'm going to give you a really basic answer, which is not going to be very satisfying. And that is because that's our agreement, that we will take angles anti-clockwise. It's just, yeah. There's a deeper answer, but it's not worth going into. Good question, though. Yeah. So we take it from there really because of our first, we call this the first quadrant. Our reference angles are always sort of facing this way already. So it kind of makes sense to continue that way because our angle is going from here. See that? From there.
So you're saying that whole angle, that whole blue angle
is from there.
Is that equal to
120. So those two angles are always going to be complementary. You know, I'm going to put a pin in that because I think it's not going to necessarily further your understanding at this point. It is taken from the x-axis in a counterclockwise direction. Yeah. So I'm just going to leave it there, Ambrosia. We can talk about it later, but I want to move on, yeah? Okay, so that's what we've got there. So we've got an extension of our understanding. I now want you to go back to your triangle there. Okay. Looking at that starter problem, ladies and gentlemen, I got you to work out that the side length of this big old triangle here is 2.73, 1 plus root 3, okay? So we know that the angle here in this big old triangle, ignoring that line in the middle, this angle here is, it's 105 degrees. Okay, now I'm going to introduce the sine rule. Now, like I did with the cosine rule, I'm stating it and getting you to use it rather than explaining how it's constructed. I haven't found one yet, but I'll put a video on Google Classroom to support that for those who are happy to spend some time finding it out. The sine rule is really simple. It's usually written like this, and I think it confuses people. And it's perfectly legitimate. The reason why people get confused is because there's two equal signs there and it makes their mind melt. All it's saying is that if you can match one side with its opposite angle and another side with its opposite angle, they'll always be equal to each other. Again, look for picture rather than the letters. So if I've got a triangle and I have an A, B, and C, then we know that the opposite, that the angle opposite that side, done it, is big C, big A, and big B. So you can see they're opposite each other. I won't put arrows in because it does make it really confusing. So all it's saying is that if you've got, say, one pair, like this one, and half of another pair, like two of these, then you should be able to work out the missing piece of information. Okay, I'm going to give you a moment to write that down, but I'll try and explain in a bit more detail. I'll zoom out again. I will do an example, I promise. So for those of you who remember permutations and combinations, this is meant to represent a whole bunch of different combinations, right? So that means A on sine A equals C on sine C, even though they're not next to each other. B on sine B equals A on sine A. It also means B on sine B equals C on sine C. All those combinations are available to you at no extra cost. It also turns out fairly simplistically, really, that sine A on A equals sine B on B equals sine C on C. In other words, you can just flip it, and it's fine as well. It still works. So what does that mean in reality? So I'm going to give you that triangle we just worked out the sides to. I know it looks tricky, but I'm going to just use the decimals to make it less tricky. So if I have a look at this triangle here, and what was that, 105 degrees? And we worked out that this was about, what was it, Rosie? 2.73. And what was this side here? And this one was 45 degrees, wasn't it? So let's leave it at that. And just for the sake of argument, let's just imagine we didn't know the angle above here. Yeah, does it not look like a 2?
No, I was making sure.
Okay, so let's just say, so we know it's going to be 105, right? We know it's going to be 105. So, but let's just imagine it's not 105. Okay? Sorry, I'll say that again. Let's just imagine we don't know it's 105. Then we should be able to work it out using the sine rule. So again, without getting caught up with A's, B's, and C's, we can say, I've got one pair I've got, looking at the screen or looking at the board because I'm pointing at things. I've got a pair that I have, a side with an opposite angle, and I have a pair with a bit I don't know. So all I do is match them up. I'm looking for an angle, so I'm going to put the angle on top. I'm going to say that the sine of theta over 2.73, please use that. Don't worry about 1 plus root 3. We know that's the exact answer though, is equal to the sine of 45 degrees over 2. So this is a standard equation with a single unknown. So you'll need to isolate sine of theta and then do inverse sine to work out what theta is. Okay, I've led you as far as I can go. I want you to have processing time, so you've got a minute and a half to get that solved. If this is fractions are scary time, it probably means you need to practice algebraic fractions, and it's up to you to do something about it.